All right, in chapter 23, we are going to focus on nucleophilic addition elimination reactions. Again, because we did that in the last chapter. But specifically, we're going to look at reagents that are weakly nucleophilic or non-nucleophilic. I have a lot of pictures here of Kevlar. Okay. And Kevlar is a strong, lightweight, flexible material. It's commonly used to make body armor. And it's produced from an amine olysis reaction, which is a type of nucleophilic addition elimination reaction that leads to the formation of an amide group. And I just want to remind you that it's this amide group here. Okay. Now, when we talk about this, the person who invented Kevlar's name was Stephanie Kowalik. And so this is a picture of her. And she was a Polish-American chemist who worked at DuPont. And she was born in 1923 and died in 2014. For her discovery, particularly of Kevlar, she was awarded DuPont's Lavoisier Medal for an outstanding achievement. And so far, she's the only female employee to have gotten that. And in 1995, she was the fourth woman to be added to the National Inventors Hall of Fame. And this particular type of chemistry is called polymer chemistry. When we talk about kind of, you can look her up. She's really interesting. And there's some videos. There's the Science History Institute, which does a lot of videos on scientists. And one of the quotes that she said is, I don't think there's anything like saving someone's life to bring you satisfaction and happiness, because Kevlar was used for body armor. So when we talk about this particular invention, right? So what happened is in 1964, people thought there was going to be a gasoline shortage, and there was. And so they began looking for a really lightweight fiber to replace steel used in tires. And so she was working with polymers, and basically the polymers that she worked with formed a liquid crystal in solution, and they needed to be something called melt spun at over 200 degrees Celsius. And she got a really cloudy solution. When she did this, it was kind of like, she described it as looking like buttermilk in appearance. And so those types of solutions were generally thrown away because they didn't work as well. They thought it would clog the machine that was used to melt spun. However, she was really persistent, and she kind of begged the technician, whose name was Charles Smullen, to test her solution. And when they did, they found out that it was really strong, right? So the new fiber wouldn't break where nylon typically would. And that was Kevlar. And Kevlar's 5 times stronger than steel by weight. So basically, she really began this field of polymer chemistry. And so while she developed this in kind of 1964, is when they started, Kevlar was introduced in 1971. Right? And so she continued to work on polymer chemistry kind of for the rest of her life. She retired in 1986. And she also served on some national research councils and for the National Academy of Sciences. She received a lot of patents in her life. Just due to her work in Kevlar chemistry. So I really love this particular invention. I think it's really interesting, obviously. But the take home message here is this is done through a nucleophilic addition elimination reaction, which we're going to learn about. Let's review nucleophilic addition elimination reactions. Basically, in step one, what you have happening is a nucleophile attacks the electrophilic atom of a polar pi bond. And so we can see how that's partially positive here. And this generates a tetrahedral intermediate. Now that's unstable, okay? And so it undergoes a tetrahedral collapse where these electrons come down and they form a double bond here, and then the leaving group leaves. And so we regenerate a pi bond here. Now, the specific reactions we looked at in chapter 22 were really limited to nucleophilic acyl substitutions where a strong nucleophilic reagent's added. For example, in a transesterification reaction, an alkoxide anion served as the nucleophile. And then in the Grignard reaction involving the ester, an alkyl or an aryl anion served as the nucleophile there. Well, here, what we're going to do is we're going to expand our discussion of nucleophilic addition elimination reactions to include ones where the nucleophiles are weak or derived from reagents that are non-nucleophilic. Fundamentally, the reactions in this chapter are quite similar to the ones in chapter 22, but there are some key differences. And we'll point those out as we go along. So, for example, the nucleophilic elimination reactions involving weak nucleophile reagents tend to proceed much slower, right? So these tend to go much slower with weakly nucleophilic reagents, right? As opposed to reactions involving strong nucleophiles like we looked at last chapter. So those are going to be a lot slower. And so as a result, they often require catalysis, right? Either with acids or bases. And so what that means for us, and generally, is that that's going to cause us to need more steps. So we're going to have more steps there. Now, most of our discussion we'll also look at reactions where the nucleophile attacks the carbonyl carbon of the carboxylic acid derivative or carboxylic acid, leading to that acyl substitution. But other things that we're going to look at in this chapter involve the nucleophilic attack at other polar bonds having pi character, like S double bonded O's. And so some reactions we'll examine are going to be functional group conversions, and then others in this chapter are going to alter a molecule's carbon skeleton. So there's a variety of reactions here, and so it's going to be really important for you to focus on the mechanism so that you can see clearly how these reactions are related. So that's something to kind of keep in mind as we go through this chapter. So in section 22.2, we learned that an ester like methyl benzoate can be produced. So we've got methyl benzoate here, can be produced from benzyl chloride here using the methoxide anion. Okay, so remember lithium's a spectator ion. And this is a relatively strong nucleophile that's being used as the reagent. And so the mechanism for this reaction is just a simple two-step mechanism like we looked at on the previous slide. Now, an ester can also be produced from an acid chloride. So this is our acid chloride, right? And we've produced an ester, and we can also do this using a weak nucleophile. So this is a strong nucleophile. And then if we go to the next slide, we see where this can happen with a weak nucleophile. Okay. And so we see here that we can treat benzyl chloride with an alcohol for an alcoholysis reaction and form an ester, but then we can also treat the acid chloride with water to produce a carboxylic acid formed here. I want to point out the alcoholysis here is a reaction where the addition of an alcohol results in the breaking of a bond. Okay. Lysis in Greek means breaking. Okay. And so in this case, it's the carbon-chlorine bond here that's broken. And so when we talk about hydrolysis, right, or hydrolysis, but it's hydrolysis is how it's pronounced, the bond in the acid chloride is broken here as a result of the addition of water. Now, what's nice about these two reactions is they occur with really similar mechanisms. So let's look at the mechanism of a hydrolysis reaction. So when we do this, we're going to draw our molecule first, right? And the first step here is a nucleophilic addition reaction. Okay, and so what's going to happen here is we have water, and these electrons are going to come in and they are going to attack that carbonyl carbon because that's partially positive because that oxygen is partially negative. And those electrons are going to jump up there onto that oxygen. Now, when they do that, I feel like I've added too many carbons. Hold on, let me redraw that. Yep. The oxygen forms a bond with the carbon, right? And then we have the Cl there. Okay, I'm just double checking my carbons. Okay, and then that's our tetrahedral intermediate. So instead of this going through a tetrahedral collapse, what happens in this stage is that we end up with a different step, which is a proton transfer. And I forgot my positive charge, so I added that there. And so during this proton transfer, what happens is that these electrons come and they steal that proton, and those electrons go onto the oxygen. And so it gets rid of that positive charge for us. Now, when that happens, right? Now what's happening is this is somewhat stabilized, but now it's going to go through a tetrahedral collapse through that nucleophilic elimination. So these electrons are going to come down here, right, and form a double bond. And then this is going to be our leaving group, and it's going to leave. Okay. So that's the nucleophilic elimination, right? And now we're left with a carboxylic acid. Okay, and so we can use an acid chloride to go to a carboxylic acid using a weak nucleophile like water in what we consider a hydrolysis reaction. Let's talk about, and by the way, the alcoholysis reaction the mechanism is the exact same. There's just an alcohol instead of that second hydrogen group, right? There's just an R group instead of the second hydrogen group. Because if we were, for example, to look at this, right, you would still end up with a nucleophilic addition. You'd still end up with a proton transfer where that proton was removed. And then instead of having this hydrogen, you have the CH3. So it proceeds through the exact same mechanism, okay? Now, when we look at these, acid anhydrides can also really readily undergo alcoholysis and hydrolysis. And when they do that, they produce esters and carboxylic acids, right? So we produce an ester here and a carboxylic acid. So these are really common reactions that change the functional group. The mechanisms for these reactions are basically the ones that were just described, right? And so, so we may think, right, that similar reactions will take place with other acid derivatives, but that's not necessarily the case. And we're going to talk about that in a second. One of the things I want to point out here is the phthalic anhydride. Phthalic anhydride right here. It's a precursor to quinoline, yellow. And this is used in foods and cosmetics. And it does have some potential health risks, but this is part of that synthesis as the precursor. So let's look at some rates of these reactions. So when we look at this particular graph or this chart, what we're looking at is that ester hydrolysis and amide hydrolysis, which are here. So what you see here is the carbon-containing species and then the relative rate of hydrolysis. And so what this is telling you is, hey, look, these are the things that are going to react with water. And if it's an acid chloride, the hydrolysis is going to really take place readily. Here is the rate. It's 10 to the 11th, right? If it's an anhydride, it's 10 to the 7th. So these take place really quickly. But when we come down here and we look at carboxylic acids and amides, these are really too slow to be useful for synthesis. Now, that being said, okay, even though the ketones and aldehydes don't undergo hydrolysis like the acid derivatives do, they can still undergo the addition of water to form a hydrate. And so that's something that we can see. So basically, here's some things that we can say in summary for this table. Okay, ketones and aldehydes are more reactive towards nucleophiles than carboxylic acids, esters, amides, and carboxylates. Okay. Ketones and aldehydes are less reactive towards nucleophiles than acid chlorides or acid anhydrides. So they're kind of there in the middle, right? Which they have popped out of the graph right there. Okay, so there's these things kind of in the middle. And so what these hydrolysis rates tell us is that the energy barrier for the nucleophilic addition increases in the order of acid chlorides to acid anhydrides to carboxylic acids and esters to amides and carboxylate anions. And so when we look at this as far as a kind of energy diagram, right, this goes in the same order as the stability ladder. And I have that written here for you, that energy barrier that I just kind of mentioned. And so notice, right, this is the same order as the stability ladder. Okay, and so that stability ladder still applies. let's talk about why we see this. So the relative stabilities of the acid derivatives are generally due to the extent that the pi electrons in the carbonyl group participate in resonance with the lone pair of electrons on the leaving group. So let's put some words to that. The stabilities of the acid derivatives are an outcome of the extent to which the pi electrons in that carbonyl group participate in resonance with a lone pair of electrons on the leaving group. Okay? And so what happens here, right, is when we talk about the resonance, you can see here these pi electrons are delocalized the most in the carboxylate anion because it has two equivalent structures. Okay, so here are the resonance structures here. For the uncharged carboxylic acid derivatives, the second resonance structure, which is shown here, where L can be any one of these, contributes less because it has both a positive and negative formal charge, right? So we end up with a positive here and a negative here, and so this just contributes less, right? So contributes less. So what we're going to see here again is that contribution by the second resonance structure decreases in the order of amides to carboxylic acids or esters, right, to acid anhydrides, to acyl chlorides. Okay, so that's where that decreases. So the second resonance structure for an ester, right, contributes less than an amide because the oxygen's more electronegative than the nitrogen, and so it doesn't accommodate positive charge as well as the nitrogen. So oxygen, right, is more electronegative than nitrogen, right? So it does not accommodate a positive charge as well as the nitrogen. Okay, so that's why we see the difference there. All right, so that ends this particular screencast. When we talk about in the next screencast, we are going to look at the aminolysis of acid derivatives. So what happens if you take these same acid derivatives and react them with amines? So in this particular screencast, we looked at, okay, here are these acid derivatives, and we are reacting them with either alcohols or waters, right? And so now we are going to look at other things that we can react them with in the next screencast.